In this lecture, we will study about creep, which is one of the phenomena because of which the mechanical failure of the component occurs. Creep is a time-dependent deformation when a certain type of load is applied. If you see this diagram, so here you have a rod and the one end of the rod is fixed firmly, and on the lower end a load is applied. The magnitude of load is such that the stresses that this load will produce are well below the elastic limit of this specimen, so it should not produce any plastic deformation. But it has been observed that if you apply load which are well below the elastic limit and you keep that load for a very long period of time, then those loads also produced plastic deformation inside the material, and this phenomena is known as creep. So a great number of high temperature failures, the failures of the component which occurs at high temperatures, are because of the creep or combination of the fatigue and creep. Generally, this creep is defined the phenomena of the plastic deformation under static loads at higher temperature, which is also known as thermal creep. But creep can also occur at the room temperature in certain materials such as lead or glass, but it occurs at a very slow rate. So time dependent deformation at higher temperatures when static load is applied such that the magnitude of load is well below the elastic limit leads to the plastic deformation in the material. So that phenomena is known as the creep. So the due to creep, the material undergoes a time dependent increase in the length, and which could be dangerous while in service. So as there is a time dependent increase in length, and every particular component, the dimensions of every particular component is designed for the respective applications, so any changes in the dimensions are not preferred while the component is in service, so it should be taken care of. So this diagram shows the creep machine. So here we have a specimen which is subjected to tensile loading. See, the bottom end of the specimen is fixed, whereas the top end is subjected with the help of this pulley with this weight. So the magnitude of the weight is less than the such that it will not produce any plastic deformation. And here this is the furnace which is provided here to increase the temperature of this specimen. So when you apply this static load for at a higher temperatures for a longer period of time, it was observed that the length of the specimen increases. As you can see in this figure, when the length of the specimen increases, then you can see that this weight has touched the base of this machine. And here also this L2 dash, the distance between these two ends will also be changed when the length of the specimen has increased. So under static loads at high temperatures, the length of the specimen has increased, means plastic deformation has occurred, and this is known as creep. So creep is affected by the load intensity, means the magnitude of the load duration, at for what amount of time the load is applied on the specimen or in the material, and the temperature at which that particular load is applied. So these are the main factors which influence the creep mechanism. Stages of the creep, if we have to see, so this is the creep curve. So creep curve actually provides information about how creep progresses with time. So creep curve can be divided into three stages: stage 1, stage 2, and stage 3. Stage 1 is called the primary creep or the transition creep, which is characterized by gradual decrease in creep speed. So here, as you can see in stage 1, the strain which is produced in the stage 1 is less with respect to the time if we compare the other stages of the creep. So creep curve is plotted strain with respect to time. So as we are considering the plastic deformation, so as a function of time we are measuring the plastic deformation or the strain inside the material. At during stage 1, the slope of this curve is higher. So during this stage the hardening effect occurs, means as plastic deformation occurs due to the dislocation movement, but dislocations pile up over one over the another, and this produces the hardening effect. So when dislocation pile up occurs, it is difficult to move those dislocations, and you need to apply some higher stresses, but as the load is constant, so here you need more time and higher temperature to produce strain inside the material. Then we have this stage 2. So one more important point about stage 1, that at relatively low temperatures, stage 1 is very pronounced, means the slope is very high. It is difficult to produce plastic deformation at lower loads, at lower temperatures, but at higher temperatures, it is easier to produce plastic deformations. Stage 2 is the secondary creep, where the creep rate is almost uniform, means slope you can see, although it is not constant, but it is uniform. It is comparatively less as compared to the stage 1. In stage 3, which is also known as the tertiary creep, here the accelerated creep rate occurs and it terminates the material into two parts, and the fracture occurs. So it is associated with both necking. So necking occurs means the dimensions at one particular particular point of the specimen, the dimensions decreases, and the formation of grain boundary and voids actually contributes to the failure of the component. Then we have another term, which is creep rupture strength. So this is the stress value which will cause fracture at a given time in a specific environment at a particular temperature. Means the value of stress at which the fracture in the component occurs, and that value of stress is also function of the time and the temperature at which that creep test has been performed. Creep mechanism, actually creep mechanism is different in case of metals, plastic, rubber, concrete, but a common mechanism we can discuss in terms of diffusion. So as creep occurs at higher temperatures, although it can occur at a lower temperature, but generally it is studied at higher temperature, because at higher temperatures plastic deformation generally occurs at a faster rate. So at higher temperature the diffusion process takes place. So diffusion is the movement of the atoms inside the materials from higher concentration to the lower concentrations. So due to the higher temperature, diffusion occurs. During diffusion the atoms move, and atoms move along the slip planes, and during the as atom moves, the dislocation movement occurs. So the hardening effects which were produced because of the dislocation pileup, or because of the pinned dislocations. Pinned dislocations are the dislocations which are stuck at some point so that they are not moving. So at higher temperature those dislocations are free to move, and the dislocation climbing and cross slipping occurs across the slip planes. So these are the phenomena which occurs in dislocations, in case of edge dislocations as well as in screw dislocations. So at higher temperature dislocation movement is free to occur along the slip planes. So as dislocation moves, plastic deformation occurs, and this result in the irreversible deformation process at lowest values of stress. So in addition, if the temperature is above the recrystallization temperature, the recrystallization temperature is the temperature at which new grains starts to form. So at the recrystallization temperatures, the grain boundary changes due to the diffusing atoms. So as new grains have to form, means atoms start to move, and during the movement of those atoms, grain boundaries also changes, and there is a shifting of the grain boundaries. So grain boundary sliding occurs, and which leads to the change in the microstructure or deformation of the microstructure, which in turn leads to the macroscopic change in the dimensions. So grain boundary sliding is more pronounced in fine-grained materials because at high temperatures grain boundaries are moving. In fine-grained materials there are more number of grain boundaries, so grain boundary sliding is higher in fine-grained materials than in coarse grain materials. All the processes which are mentioned here, likewise the dislocation gliding or dislocation movement, then grain boundary sliding, which means movement of the grain boundaries, these all are diffusion controlled processes, and diffusion is controlled by the temperature as well as the time. So these all processes take a specific amount of time in order to complete the plastic deformation. Actually, diffusion is only controlled by the temperature, but the stress which are applied are the lower in magnitude, so it will take a higher amount of time. So for this reason, irreversible deformation process, which is creep, becomes noticeable for a longer period of time. So if we have to see the effect of the grain size, then we can define the creep mechanism into majorly into two groups. First is boundary mechanism, in which the grain boundary moves. So if the grain boundary is moving, then this mechanism is affected by the grain size, because if grain size is more, then grain boundaries are less, and if grain size is less, means there are more number of grain boundaries. So creep mechanism occurs due to the boundary slidings. And another one is the lattice mechanism, where atoms move inside the lattice. So creep can come to halt due to work hardening if the temperatures are well below the recrystallization temperature. So at lower temperatures, the dislocations stuck, and these are there, the movement of the dislocation is difficult. So creep also comes to halt at those point of time. So in such a case, fine-grained microstructures show better strength values than coarse-grained microstructures due to the grain boundary hardening. So as grain boundary also serves as a hindrance, so at low temperatures, the dislocations are difficult to move, and these are also stopped by the grain boundaries, means this movement of the dislocation is also stopped by the grain boundaries. Because the temperatures are low, grain boundaries cannot move, and those grain boundaries are also helping for the dislocations to stop moving, and which in turn is reducing the creep. However, above the recrystallization temperature, strain hardening effects, means this work hardening or strain hardening, which is due to the hindrance in the dislocation movement, that is absent. And due to the better resistance of the grain boundary sliding, coarse grain microstructures show better strength values than fine grain microstructures. And for this reason, grain boundary free materials are used for thermally and mechanically high stress turbine blades. So above the recrystallization temperature, what occurs? That dislocations start to move, as well as grain boundary also start to move. And if there are more number of grain boundaries, then the more plastic deformation will occur. But if grain boundaries are less, then less number of grain boundaries will move in comparison to the fine grained microstructure. And less grain boundaries are moving, means plastic deformation is comparatively less. That is why at higher temperatures, the grain boundary free materials, which are generally single crystal materials which do not have grains in them, or likewise nickel based superalloy is a type of single crystalline materials, those are used for highly stressed turbine blades, means blades which are subjected to higher temperatures. In those cases, we use materials which do not have grain boundaries. So here this diagram shows the creep curve. So at the low temperatures, the creep curve will be having a lower value. At the medium temperatures, you can see the strain is somewhat higher in comparison to the low temperature uh, creep curve, but at the higher temperatures you can see that the strain is very large in small amount of time. So when the temperature is increased and stress is increased, the strain increases at a higher rate. So it means that rate of creep increases as we increase the value of stress, means magnitude of load, or the value of temperature. At the higher temperature and higher stress value, creep increases. This diagram shows the jet engine turbine blade which has failed due to the creep failure, and the creep failure has occurred due to the intergranular cracking, means crack propagation of crack along in grains, and this is the direction of the stress. So this is the photograph of the turbine jet engine turbine blade failed due to the creep loading. So constant load at higher temperatures produces creep loading. If you increase the magnitude of load or the value of the temperature, then creep will propagate at a higher rate. So this was all about the creep and its mechanism. Thank you.